This video is a quick tutorial about how to work Hardy-Weinberg problems. Hardy-Weinberg problems are used to find the genotypic frequency and allele frequencies in a population. It's important to know what the different variables in Hardy-Weinberg problems stand for. P stands for the frequency of the dominant allele, Q for the frequency of the recessive allele, and then if you're looking for genotypic frequencies, P squared is the frequency of the homozygous dominant genotype, 2PQ is the frequency of the heterozygous genotype, and Q squared is the frequency of the homozygous recessive genotype. So there's 4 easy steps to finding the allele frequencies, P and Q, in a population. There are 4 easy steps, and we're going to practice these. First, you're going to count the number of recessive phenotyped individuals. Then you're going to calculate the percentage of recessive individuals in the population. That is going to be the value called Q squared. So there we go. Now we have the genotypic frequency of individuals with the homozygous recessive genotype, Q squared. Great. And so now, though, we need to find Q. And that's really easy because all you have to do is take the square root of Q squared to get Q, the allele frequency of the recessive allele. Then to find P, right, the allele frequency of the dominant allele, you just use the simple equation P plus Q equals 1, right? Then rearrange it to where P equals 1 minus Q, the value that you just found. And so now you have both P and Q. So here's an example. If 40% of a population shows the recessive phenotype of whatever trait, then Q squared equals 40% equals 0.4. Then we take the square root of that to get just Q, which when we do that on our calculator is 0.63. And then we use our P equals 1 minus Q to determine P, which is 0.37, or 37% of the alleles are dominant. To find genotypic frequencies, right, this is our P squared, 2PQ, and Q squared. First, you want to calculate the allele frequencies using the steps from the last slide. Then you're going to use those allele frequencies in the equation P squared plus 2PQ plus Q squared equals 1. So let's work this example together. So we'll use the P and Q from the last problem. So to find P squared, or the frequency of the homozygous dominant genotype, we just multiply P times itself, right? So 0.37 times 0.37 will give us 0.14. I like to round to the hundredths place. All right, and then to find the frequency of heterozygotes in this population, we multiply 2 times P, which is 0.37, times Q, 0.63, equals 0.47. All right, and you can do Q squared a couple of ways. A, you can just look back at when you were finding the allele frequencies, because Q squared was the first thing you found. Or you can just multiply it. Or, since P squared plus 2PQ equals, P squared plus 2PQ plus Q squared equals 1, you could subtract these values from 1 and get Q squared. Either way, I'll just use my calculator here to do Q squared, so 0.63 times 0.63 equals 0.4, or 0.39. And if you add these values together, they will equal pretty close to 1. So here's a quick practice problem. So cystic fibrosis is a recessive condition that affects about 1 in 2,500 births in the United States, in the Caucasian population of the United States. Now this problem wants us to calculate the frequency of the recessive allele, the frequency of the dominant allele, and the percentage of heterozygous individuals in the population. All right, let's try and do that together. All right, so number one, the frequency of the recessive allele. First of all, we just need to figure out, well, what does that mean? Right, and the frequency of the recessive allele can also be written as Q. So it's easy to find Q because we know how many recessive individuals there are. So the problem told us that 1 in 2,500 births have cystic fibrosis, which means 1 in 2,500, so let's do that together. 1 divided by 2,500 equals 0.0004, all right, have the homozygous recessive genotype, which is also Q squared. So we can say Q squared equals 0.0004. And so to find the Q itself, we just take the square root of Q squared. So I'll push my little square root button, and that gives me that Q equals 0.02. So I've found the frequency of the recessive allele, Q. It's 0.02. All right, and then it wants us to find the frequency of the dominant allele. So if we know that P plus Q equals 1, and we can rearrange that to say that P equals 1 minus Q, and we know Q right here. So then P equals 1 minus 0.02, which means that P equals 0.98. And that makes sense because 0.98 and 0.2 equal 1 when we add them together. And then finally, it wants us to, now that we've found the allele frequencies, it wants us to find the percent of heterozygous individuals in the population. Okay, so this has a couple of steps. First of all, to figure out the percent of heterozygous individuals, that's going to be the same thing as 2pq. All right, that's the frequency of heterozygous individuals. So we use 2 times p 0.98 times q 0.02, and we're just going to use our calculator here to do 2 times 0.98 times 0.02, and that tells us it's 0.04. .04 of the individuals in the 0.04 is the percentage of heterozygotes that are in the population. Now, if we wanted to take it a step further and figure out, okay, I'm just going to have to edit this out. Awesome, that's no problem. Okay, keep going. And then our last practice problem says the allele for widow's peak hairline is dominant over the allele for straight hairline. In a population of 500 individuals, 25% show the recessive phenotype. How many individuals would you expect to be homozygous dominant and heterozygous for the trait? So, what does it tell us? In a population of 500, 25% show the recessive phenotype. Okay, well, how many is that? So 25% of 500, right, is 125 individuals. Great. All right, but this straight up tells you Q squared is 0.25. So, okay, I'll cut this out, and cut, and action. In our population of 500 individuals, 25% show the recessive phenotype. So it just gives us Q squared right there. So Q squared equals 0.25. Great. How many individuals would we expect to be homozygous dominant and heterozygous for the trait? All right, so these words describe genotype. And if we remember, to get the genotypic frequencies, we have to first find the allele frequencies, which is super easy. Because if we have Q squared as 0.25, all we have to do is take the square root of 0.25 to get Q. 0.25 square root 0.5. So Q equals 0.5. And if Q is 0.5 and P equals 1 minus Q, then P also equals 0.5. Fantastic. All right, and so now that we have our allele frequencies, we can plug those in to try and find, right, P squared. This is our frequency of homozygous dominant individuals, right? And heterozygous, that is 2PQ. And that'll give us the percent of heterozygous individuals, right? So let's just do that math. P squared, right? 0.5 times 0.5 equals 0.25, right? That makes sense. So P squared equals 0.25. And 2PQ, right? 2 times P, which is 0.5, times Q, which is also 0.5, equals 0.5. Right? And that works out because P squared plus 2PQ plus Q squared does equal 1. So that's how we know that works out. But the question asks us not what percentage, but how many individuals. So now we have to use these percentages and apply them to the number of individuals in the population, 500, to find out how many individuals would have each of those genotypes. So to do that, we want to take, we want to do 0.25 times 500, right? 25% of 500. And then to find how many heterozygous individuals, we're going to take 0.5 of 500. Now that's really easy. 0.5 of 500, we can do it on our brain. Half of 500 is 250 individuals. All right. And then, well, 0.25 is half of 0.5. So this number is going to be half of that number. Or you can just do it on your calculator to be sure that that's true. Right. 0.25 times 500. Right, is 125, right, which is half of 250. So the answer to these questions, right, how many individuals would we expect to be homozygous dominant, right? So 125 individuals would be homozygous dominant, 250 individuals would be heterozygous for widow's peak. So those are just some examples. You can find a zillion other practice problems on the internet, but hopefully using these strategies, you will be able to work some problems of your own.